Hello friends, I am Saroj Vishwas, gold medalist, first rank holder of 1994 batch in engineering stream of all the colleges affiliated to University of Mysore during that period. A BE in civil engineering from National Institute of Engineering Mysore, a MTech in structural engineering from Indian Institute of Technology, Delhi, that is IIT Delhi, a Sun certified Java programmer, Sun Microsystem USA. I have more than 25 years of professional experience in designing building structures and allied subsidiaries. I invite you all to learn with me how to design building structures using commercially available structural softwares with the help of some manual computation as and when needed. Having gone through the architectural requirement or the requirement provided by the customer, the structural engineer now must devise a framing plan to provide a load path mainly for two kinds of load. There is gravity load and the lateral load. The gravity load consists of the dead load or any other kind of superimposed load and live load. The lateral load consists of wind load or the seismic load. In addition to this, the frame must be able to resist the pressure or thrust generated by wind load or by the components of seismic load. The drawing on left hand side shows the framing plan to carry the lateral gravity load of the mezzanine floor. So these are the main girder. This main girder in turn supports this joist, which in support this deck slab. These are also main beams, but these are simply supported main beams. It helps to transfer load similar to the joist while it transfers the gravity load, but its behavior changes when it's transfer the lateral loads. So these joists are spaced 1.5 meters center to center, assuming that our deck sheet will be 0.8 mm thickness with 45 mm of corrugation. This type of deck is able to resist wet concrete load up to 150 mm depth. So to resist that kind of load, the usual spacing is 1.5 meter or less. So we are planning to provide this joist as 1.5 meter center to center. The drawing on the right hand side shows the framing plan at the roof level. The roof contains concentric basing at roof level. These are the concentric basing. In PV structures, mostly rod basings are provided, but rod basings are not able to carry axial compression, so they must be a specified tension only member in STAAD Pro. However, for our buildings, we shall take this as a pipe member or tube member and specify these members as truss. So a truss is nothing but which can carry both axial compression and tension. The reason being that we'd like to perform a dynamic analysis for this building so that we learn how the dynamic analysis is to be performed with STAAD Pro. The issue with the dynamic analysis is that in dynamic analysis, response spectrum method is specified in the code and time history method is specified code. Mostly the response spectrum method is used by the structural engineers. So in response spectrum method, there is a CQC method to work out the base shear, Base shear is the total seismic load that will be generated during a seismic occurrence. So, in sequencing method, the signs are lost, and to use tension members, we need to preserve the signs. Now, since in response spectrometer signs are lost, so it is difficult to perform dynamic analysis with response spectrum method with tension only members. One important thing is to note the difference in orientation between the column at the grid intersection of 2 and A and grid intersection of D and 2. So, see, this column is oriented in such a way that the wind pressure or any lateral component of the earthquake will be resisted by the major inertia of this column, because this column doesn't have a support at mezzanine level. So this is a double height area. So this column will have a support at bottom, and it will be restrained by the roofing frame at top. So it will be a double height column. So it is prone to local deflection. So the orientation of the column has been kept in such a way that its major inertia. This is the I column. So if we see the major axis, this is the major axis, major. So the inertia about the major axis is the major inertia. Major inertia is utilized to resist the load. A special consideration must be taken while we model the stringer for the staircase. See, this is the line of the riser of the last step. So the secondary beam or the secondary girder which is supporting this stringer must be kept bit away from this line, this last line of the riser. This is to accommodate the connection details. This kind of connection details are provided in bolted structure. Even if it is welded structure, some space will be required for welding. So for our model, we plan to keep the center of the secondary girder which is supporting the stringer at 450 mm away from the last line of the riser. Next, how would we plan the frame to carry the lateral load to foundation or to provide a load path for the lateral load? Now the lateral load along x-axis shall be resisted by moment resisting frame. This is the model, the 3D view of this building has been placed, how we are going to model in the STAAD. These are the global axis of the STAAD, y-axis, x-axis and z-axis. So along x-axis, the lateral load will be resisted by moment resisting frame. In moment resisting frame, the lateral load is passed to support through flexural action, that is bending moment. Through bending moment, the lateral load will pass to the support. In z direction, the lateral load along the z directions will be resisted by concentric bracing. These are the concentric bracing along grid A and along grid 1 and along grid 3. The bracings are provided between grid B and C. So whatever lateral load is generated because of wind or because of earthquake or seismic regions, at the roof level they will be transferred to the roof level bracings through studs and ties and a flexible diaphragm provided by the roof sheeting. While at mezzanine level, they will be transferred to this concentric bracing through deck sheet or semi-rigid concrete diaphragm that is being provided by the concrete deck slab. These beams and joists. This flexible diaphragm a roof sheet usually provides a flexible kind of diaphragm, will transfer the lateral load through the moment resisting frame along x direction, and these beams and the semi-rigid diaphragm. A semi-rigid diaphragm is nothing but a actual stiffness of a deck slab in lateral direction is called semi-rigid diaphragm. A rigid diaphragm is something which is entirely rigid. It has got a rigid body movement. It moves like a rigid body. The whole of the system will move. Stiffness doesn't play any role while the movement, but in a semi-rigid diaphragm, the stiffness have roles. How much the slab will move along a direction. So this semi-rigid diaphragm provided with the metal deck concrete shall provide a load path to the movement frame along x direction. So now we have devised framing scheme to provide a lateral load path for along both x and z directions. Next thing we need to discuss is the modeling constraint in STAAD. STAAD uses central line method of modeling. So we must compute the center to center distance between the of the columns at ground floor level or first floor level, assuming that the bottom of the base plate shall be at 250 mm below the finished floor level. We are providing 250 mm because we might have to accommodate some stiffener here. So stiffener has to be below the FFL level at ground level. So assuming that the base plate, bottom of the base plate shall be minus 250 mm, the column height for STAAD works out to be 3.125 meter at first story and 3.880 meter at second story. For preliminary modeling, we can assume the depth of the girder as span by 15 and depth of the rafter as span by 20 or span by 25. So rafter is nothing. It is a structural member which supports the purlins and which in turn supports the roofing sheet. So in PEB industry, these members are usually called rafters, which supports a sloping roof using purlins. One more thing, we shall not use chapter 12 for this building. We have excluded chapter 12 here. Chapter 12 itself is a vast topic, so we can take it up in some other tutorial. So as of now, we shall exclude chapter 12 requirement, but obviously we will model this as a ordinary movement frame or ordinary concentric frame, but without following the detailing requirement of seismic detailing requirement of chapter 12. Usually in market, provisions of chapter 12 are adopted only when it is specifically asked for by the customer. Otherwise, the difficulty in detailing is quite cumbersome if we try to use chapter 12. So many times we do not use chapter 12, and instead we actually reduce the response reduction factor parameter in seismic loading, thereby and keep this value around 3 or 4 as per ordinary movement resisting frame or ordinary concentric basing frame. Thus actual seismic loading is increased by 33% or 66%. Next, we shall discuss the gravity loads that will be applied on our STAAD models. For a office building, generally 125 mm thick slab is advocated. I have already told that we will assume a 0.8 mm thick deck slab with 45 mm corrugation. So the effective depth of the concrete shall be 125 minus 45 by 2. Further, we have considered 1 kilonewton per square meter for light partition, because the partitions drawings is not available as of now, and it is being planned for future. So we have taken 100 kg per meter square as specified by code. That is the minimum value of partition load. Further, there will be wall load. Wall load due to dry wall, usually light gray. These are the wall load magnitude, which has been worked out as per usual specification that is being used in market. So our wall load works out to be 2 kilonewton per meter for walls, which will be along x direction. Which will be along z direction. Along x direction there will be gavels, so wall height will be varying. So on the average, we shall take average height and work out the wall load accordingly. So it comes to be 2.17 kilonewton per meter. Next is wall cladding load. The wall cladding load works out to be 15 kg per square meter, or 0.15 kilonewton per meter square. Then there is a roof sheeting load that also works out to be 0.45 kilonewton per square meter. Then the live loads. The live load is specified in the code for office uses is 4 kilonewton per square meter. Then comes the live load at roof level. Our is this metal sheet roofing, where no access has been provided. So our load will be 0.75 kilonewton per meter square. We generally in PV building 1 in 10 slope is provided for roof sheeting. So this works out to be 5.7 degree. So 5.7 degrees is less than 10 degrees. So obviously we have to go along with this value, that is 75 kg per square meter. Next, we shall discuss what kind of support we will provide to our column. There could be 3 types of support: a fixed support, hinge support, and partially fixed. A fixed support is able to resist movement, shear, and axial force. A hinge support is not able to resist any movement. It can only resist shear and axial force. But practically, there is no support is 100% fixed and no support is 100% hinge. But for design practices, to make the design bit simpler, the usual assumption is to consider the supports as either fixed or either hinge. There could be a partially fixed support, but that is the advanced topic, and that is usually not considered in routine design. Next, we have 3 figures: 1, 2, 3. The figure 1 shows anchor board arrangement in which the column support is fixed about one direction, but it is not fixed about other direction. It is fixed about one direction, it is not fixed about other direction. The figure 2 is the anchor bolt arrangement for a hinge support, that is, it cannot take any movement in any of the direction. And figure 3 is fixed support in both the direction. It can resist movement in both directions. Usually for I column, this type of support is taken. For box column, fixed support at both the direction is usually considered. So in our case, we shall have I column. So we shall have this kind of column. We are planning to provide support system that will be fixed about Z axis. That is, it will be able to resist movement along global global x axis of stud, and it will not be able to resist movement along global Z axis. As per plant requirement, that will produce minimum strength, we follow certain wave depth and certain flange width. Wave are kept in multiple of 50. That it could be 200, 250 to 300 or 350 and so on, and flanges are kept in multiple of 25, that is 150, 175, 200, 225 and so on. However, while deciding on the width or depth of wave plates, we have to keep the code constant. Code provides certain W by T ratio for the plates, so that section is classified into plastic section, compact section or semi-compact sections. STAAD can design up to semi-compact flanges. Although the code provides provisions to design slender member, our STAAD has not implemented that yet. We shall not model built-up section to start with, because to provide built-up section, we have to use a tapered property from the STAAD Pro. The issue with the tapered property is that whenever we divide a tapered member, a lot of section properties are created in the property dialog box. So it's become difficult to keep it trail which which size is for which member, because it's for same size of the member, a lot of member property is created in member property dialog box. So a built-up member is nothing but a wave plate we welded with 2 flange plates in I sections, in case of I sections. So to start with, we shall proceed with a standard section such as ISMB, and later we shall change this to built-up section when we have done all the loadings, when we have supplied all the design parameter, etc. This ends the required information that we need to start preparation of the geometry or actual modeling in STAAD Pro. So let us see you in the next section, that is modeling with STAAD Pro.